Good afternoon. This is Mark Richardson with Vibrant Technology, and I welcome you again to another MEscope ODS Videos webinar. And I hope everybody is doing well and staying safe. Again, we are joined by Dan Ambrey from Full Spectrum Diagnostics, and today Dan is going to go through a webinar titled Getting Started with ODS Videos. And in this webinar, we are going to spend a great deal of time looking at the ODS Videos wizard and kind of walk through each of the steps, talk about sort of best practices for using the ODS Videos wizard and setting up your animation and different tips and tricks. Few things before we get started. Housekeeping notes. We are recording this webinar, so if any time you want to go back and review something you may have missed, you will be getting a full recording of this at the tail end of the webinar. In addition, we will open it up to some questions, and we'll, given how much time we have left, there's probably going to be at least 10 or 15 minutes. We should have time for a few questions. But if you have questions, feel free to type those into the questions box in the GoToWebinar panel there on the right-hand side of your screen. With that, let me hand things over to Dan, and we will go ahead and get started. Dan, take it away.
Hi, good morning or afternoon to all of you. Welcome to another episode of MEscope ODS Videos webinar. What you're seeing on the screen here is a setup for imaging. It's called a spray pump, and it's basically an ash slurry that it's pumping out of a big structure, that a big tank, a holding tank. They grab the fly ash and they water it down so that it will all stick together and it'll turn into a fluid that can be pumped. Very dirty process. They have dozens of these pumps, and they had all kinds of service problems with them because it's a very corrosive environment, but also it was a very poor design. If you look at the platform, and I have another view of this that I can show you, but the motor sits on top of this kind of cantilevered platform. This area right here isn't really connected to anything, so everything's pivoting off of that point. There's a smaller sheave on this side and a big sheave on that side. It's a 2.5 to 1 reduction. So it's an 1800 RPM motor, and it goes down to about 700 RPM on the pump side. So when you have a system like this that's very flimsy, that has a lot of rotating sources, there's a lot of frequencies that are generated. And that's one of the things I really wanted to concentrate on in this webinar, is how much resolution do you really need? You can do a quick video, but how quick is too quick before you start merging things together and not getting the true motion of the machine? We're going to go over that in some detail. The kind of background information: many production-related machines can't be shut down for natural frequency testing or resonance analysis. And in those cases, operating deflection shape makes us a good compromise. We can see the actual operating responses of the machine. In this case, there's 3 different rotating components: the motor speed, the belt speed on the reduction sheave, and then the pump speed going out. And they all have harmonics, and there's blade pass, and there's plenty of things to animate to better find the underlying causes of the problem. But if we don't have enough resolution, we're not going to be able to tell which frequency corresponds to which. And it'll make more sense when I show you some of the spectrum that we pulled off of this. The MEscope ODS Videos, it's a high-speed video vibration analysis. The video clip is processed with an optical flow algorithm. It enhances the subtle displacements and rescales the amplitudes. So now it's something that you can't perceive with the human eye is very visible. And you'll see some motions here and you'll think, wow, it's really moving. I cannot see that motion unless it's above 4 mils, 4/1000ths of an inch. And most of the response in this machine is less than 4/1000ths of an inch. So it's pretty amazing how much motion you can pick out and what the shapes look like, and very interesting. So we'll show you what some examples are, and we're going to run through the wizard, and we've had a lot of changes to the wizard, and we're going to use our spray pump here as the analysis tool to show us what's going on inside that wizard and how it's laying all the cards out for us. There we go. I did do an operating deflection shape analysis and a modal analysis on this same unit a couple years ago, so I knew quite a bit about it. But some of the things that you should be interested in frequency-wise are listed here. And remember, there's 3 rotating systems. There's the pump rotation, there's the motor rotation, and there's the belt rotation. What we're going to see in our spectrum, we're going to see harmonics of the motor, we're going to see harmonics of the pump, and I'm showing 4 pump harmonics, 2 motor harmonics, and a bunch of belt frequencies, but they all say 2 times belt, 4 times, 6 times. In all actuality, if you have a crack on a belt or something, it's hitting both pulleys every belt revolution. So you're actually, the biggest bump for the money is the 2 times belt frequency, because there's 2 events going on every revolution. Regardless, there's a lot of frequencies here. There are 9 different frequencies in a relatively small span, 3,000 CPM, okay? I have a couple of measurements here, and the top one is 0 to 12,000 CPM and is at very low resolution. It's like something like 0.05 seconds. And basically it's a scanning mode. I'm just looking at a rough shot at the whole system. I don't really know what I'm looking at, because there is definitely not 9 peaks within this section here. The bottom plot is about a second's worth of data. So you go from a very quick analysis to something that takes a little bit longer time, and you can see all the different peaks pop out. And now we have a better idea of what's going on. The more time we take, capture in the number of frames into the analysis, the more detailed we're going to be able to get as far as the peaks in the spectrum, okay? So as I mentioned, belt drive driven pumps include rotating frequencies of the shaft, the pump shaft, the motor shaft, pump shaft, and the drive belt itself. We're looking for unbalance, misalignment, looseness, blade passing frequency, and resonance, okay? There are a lot of faults that we can't detect with ODS videos, but these are the faults that have phase associated with them. So the structure will go into a standing wave or a mode shape, and it's discernible, each frequency. So before we get too far into that, let's quick go through how much is too much resolution. So we're talking, are we wasting our time, or what's going on? I have been using the entire buffer for the vibration analysis. Inside the Chronos camera, it gives you a ring buffer that's 8 seconds long. So I can record 8 seconds worth of vibration, then it'll overwrite itself. And I've been using it as a more of a stability or a jitter control, where just touching the camera will make it bounce a little bit on the tripod. If I capture 8 seconds worth of data and then let it start overwriting, I'll get rid of that little transient response. So every time I start or stop the camera, there's a little bit of bump in the time domain, okay, that I will pick up, and it'll influence my data. So there's different ways to control jitter, but now I'm looking at how much do I actually need? I don't really need that 8 seconds, even though I'm using it for a different purpose when I record it. But what exactly is it getting me? And as far as resolution, I have several different examples here. The top plot, well, this one was taken at 0.05 seconds worth of data. You get a really crummy looking time waveform and a really broad band spectrum. There's not a whole lot associated that you could really pull out of this. In fact, this large frequency is the combination of 5 or 6 frequencies that I should be seeing, and the same here. So looks like right now this would be way too small a window of data to get anything meaningful. But if you go and look at the animation, you say, yeah, that has some motion to it. But as we'll see in a second, if we walk down here, there's no standing wave in this 0.05 second video that compares anything like 1 second worth of data. So as we take longer and longer chunks of time, we get a better representation in the ODS video, okay? And we get better resolution in the time waveform and the spectrum. So we have a 1/10 of a second, we start to see peaks showing up that are not just glommed all together because we have poor resolution. This is 1200 CPM per line. This is twice better than that, 600 CPM, and we keep going down. So as you can see, as we get to here, about 1 second's worth of data, we're really defining a lot of peaks that we should be interested in. We get nothing here, and about 1/2 a second, we start picking out things with good resolution. 1 second, it's even better. Okay. These are all the resolutions that we're going to get. So 1 second looks pretty good. That's 60 CPM per line. If I'm doing an analysis with accelerometers and doing an ODS analysis, I will choose 500 Hertz or 30,000 CPM as an F max and 800 lines on most standard equipment. What that equates to is about 37 CPM per line of resolution. So even 1 second worth of data isn't quite there. So I'm looking something closer to 37 would give me a good frequency response. I'm already getting a good animation, but I want to be able to pull all the frequencies I can out of this before, I don't want to combine peaks and give myself a false indication of the problem. This is, I couldn't fit it all in one page, but this is interesting. This is 1 second worth of data that we just left on the other page, 60 CPM per line. Approximately 1.5 seconds is where an accelerometer would see the data, okay? Any longer cuts at it I take, the peaks get better and better, and I pull little peaks in between out. So I do get much better looking data at 8 seconds, but the animation doesn't really progress any better than that. So if I'm doing my analysis, I should be doing it at about 1.5 seconds instead of 8 seconds. This might take 20 or 30 minutes to collect this data or process that video. This might take 3 to 4 minutes, where I'd get a good spectrum, I'd get a great animation, and I'd get the proper resolution that I'd get with a normal accelerometer analysis. Okay, I just say that because we're going to do some stuff in the wizard that talks about how many seconds worth of data should you process. This whole little exercise here, it leads me to believe it should be somewhere between 1.5 and 2 seconds worth of data. Okay, if you keep that thought in your head, when we get to the wizard, it'll show itself in a different way. Camera and lighting, and one of the things I've been telling you guys over and over again, you should take a picture of your setup. And there's 3 different setups that I did for this spray pump. One was perpendicular, so I'm looking 90 degrees from the motor indication. I don't have it listed here. This is the 45 degree view, and then this is the 0 degree view, or straight in from the side. And my angle here isn't the same as what's being captured on the camera, but this ledge where the foot is, which is that frame there, that's what I'm trying to get. And I tried to blow it up in this little inset picture. There's the line. So I get a really good straight on shot of that platform, and I can see if the platform's flexing or the foot's loose or something's buckling in there that shouldn't be, okay? We'll talk about the wizard. The first thing that we actually do is not adjust and crop, but we actually open the raw video, which is this little box here. If I click on that, it brings me into my files, and I can go hunt for which one I want to open up, and this is the one I found. This is that spray pump, and I had to turn the camera. If you remember, my camera is 90 degrees from where I normally take the image, so it comes in at that angle. It wants to put it in the other direction. So that's okay. We can rotate it. We can fix it. There are several different adjusting and cropping type tools that we can use. The one to the left here is minimize flicker. If you have LED lights, the cheap ones, you're going to get flicker, and it's going to look like there's a strobe light going off in the background. You want to avoid that and get better LED lights, but the minimize flicker will also help somewhat. There's only so much you can do with Home Depot lights. You really have to go to special places on the internet to pull those off. We also can rotate the image. So I'm going to rotate it out of plane here. So set it up the way it's supposed to be. We can adjust the brightness and the contrast. The contrast is usually the only thing I need to move. And actually what you're doing right now is setting up a quick video. So when you start to check all these things off, the next time you come through here, you can just click quick video and it will set it all up the same way again. So flicker, rotation, contrast, and brightness, we can crop it and we can reset the crop and do whatever we want. I could zoom in on this ledge independently, and you don't get any better resolution. Your resolution set by the entire field, which is 1024 by 1280, but you can zoom in. The best zoom is to take another video, to use the lens of the camera to zoom in, or setup of the camera, and now concentrate all your pixels in a certain frame. Okay, so first thing we're going to do, I would normally rotate it, but I did something out of order here. I will play with the contrast and get it to a nice color view. There's multiple cameras out. The Chronos cameras that we've been recommending from Canada, they have a monochrome or black and white version of their camera, and then they have the color version. And it's a preference. They both do very well, but the color looks good for me. I really like how it turns out. So here's the changing the contrast, gets you a better color representation. There it's kind of dark and dirty, and then it brings out the contrast quite well. This is rotating. It was on 0 degrees rotation, so I just turned it to the 270 position, and now we're up exactly how I was viewing it when I collected the data. This is the cropping feature, and I mentioned it doesn't change your resolution. It won't concentrate your resolution into the new cropped field. It just cuts out background stuff that you might not be interested in that was in the original image. And the one thing I probably could, this is a little smudge or a shiny spot, something in the background, maybe some dust on the camera lens that will show up in the animation as kind of something with a lot of motion. So there's another way to get rid of that, and we'll talk about that in a second. But the cropping feature could just cut it right out, but it's a little too close to this ledge, so I opted not to do that. This is a little bit about the frames and duration. What you need to tell the software is what kind of video dimensions you have. I believe it defaults. It knows from the video when it comes in, but it does not know the frame rate. The frame capture rate is set up in the camera, and that's determined by the user, and it's going to give us an idea of how many seconds of data that we have. So I have 8 seconds worth of data that I've recorded. I can get my frame rate from 2410 minus 296 will give me twice the frame rate. So what is it, 1114? 20, whatever. Yeah, you know what I mean. I'm getting ahead of myself a little bit. As we adjust these sliders, I can start at 0. In this case, I didn't. It started a little bit higher. 0 to some value of capture rate will get you a time scale, and this will automatically change as we move these sliders along. So I've decided I'm going to do 2 seconds worth of data. That's going to give me a nice resolution without waiting too long for the video to be processed. Once we do that, we want to set some type of scaling distance. This is the set distance command. It's a 1, 2, 3 process. I'll click on set distance. It'll erase whatever distance was already in there and allow me to draw a straight line from a known point on the screen. So this foot that you're seeing right there is 3/4 of an inch thick. So I have that hunk of steel. So I drew my little image here, put in, yeah, that represents 3/4 of an inch. Make sure my units are correct, and it'll scale my amplitudes properly. This is the grid point frame, and we can set this to whatever we want. It has a pretty much coarse frame on it right now. We can make it much finer. The reason we have this is we can't show you all the data. If you think about this, 1024 by 1280 is 1.3 million pixels on the screen, a little bit over that. We can't collect a time waveform for 1.3 million pixels. It would take too long, and it would be so much data that we wouldn't know what to do with it. So instead, the optical flow algorithm works really well with this grid points. So we're basically making a visible structure that's equally spaced points on a grid that we're going to interpolate to. So all those very high numbers of 1.3 million pixels are interpolated to whatever grid point coarse or fine setting that we have set up. Okay, so it defaults to a coarse grid. You can zoom that or slide this over to get better resolution. That's in the next one here. So I've pretty much quadrupled my resolution in the coarse to fine measurement of this grid. Now, same thing, all the pixels are interpolating themselves to the closest grid point. Okay, so in that case, instead of having 1.3 million equations that I have to write, it's 4,636 in each of the X and Y directions. So about 9,000 animation calculations going on here. And this is a pretty fine grid. What I like to do is the part that I'm interested in is this ledge going down right there. I want to see how it deforms. I want to have one of these grid points going somewhere all the way along that grid or all the way along that ledge so that I can see exactly how it's moving. I hit the extract time waveform button, and now after it processes all the data, I get filtered displacements. So the displacement here is shown as a histogram. So I have large number of motion is in the middle of this. As you roll off of this side, I have a large number of small displacement, and that's background noise. That's stuff around the edges that I'm not really interested in that go dark. If I get rid of these, it'll crop out some of that data for me. This side is a small number of large displacements. So shiny spots, exposed rotating shafts, swinging chains, like I had a couple of valves that had labels or a little tag on them that was hanging by a chain, and the whole thing was swaying. It shows up in the animation as a big displacement, but it's not anything I'm interested in. If I take my slider and move it this way, I can get rid of those large displacement shiny spots and exposed shafts and things like that will come out of the data, and I won't have distortions in it. And I can do both if I'd like. This is an example of just pulling the large number of small displacements, the background noise, and getting rid of a lot of that. This was looking down a hallway that just goes black. This was some of the structure on the foreground, which was part of the pump housing. Nothing that I really want to see. I want to see the motor and the structure holding the motor. I can grab the other one and drag it in, and now I'm getting the shiny spots, the different areas that I could be interested or could not be interested in. In my case, I want to see this platform, so I don't want to take these spots away. So some of the shiny stuff I'm going to have to live with. Okay, so I go back and I did them all. And at least my first cut, I usually do an entire thing, and then I'll I'll go in and reprocess the data later. We get to this page. This is the point graphics, and this is a real nice addition to the wizard. It's been in some of the early software, but as a little computer routine or a hotkey. All the commands are already in the MEscope software, but putting all the commands together and getting a process or a quicker succession of different commands really helps. So we call those hotkeys, and we had some hotkeys for doing orbits and for doing vectors and labeling and things like that we're seeing here. But now they're baked into the software, and they're part of the wizard. Okay, there's only one that's missing in this, and I think it's going to be in tomorrow. Every Friday they do a build of the software with the latest stuff that they put into it. And this was last week's, and they made a lot of big bounds in the software since then. But anyway, there's several things. There's labels, which are X and Y labels for each of these points. They're in blue right now. There's magnitude and phase labels. They will give you the actual motion of the grid point in here and what phase it has on the screen. There's a vector plot, which is shown down here, which will give you arrows and gives you a really good indication on what the motion looks like, how the flow of the motion. And also there's an orbit plot, and the orbit plot's very similar to the vector plots, but it'll show you how much XY motion that you have. Remember, this is two-dimensional. This is vertical and horizontal. And if we shoot at an angle like this, we get exactly what the vertical and the horizontal motion is. If we shoot it at a 45-degree angle, we have that implies some depth, and we don't have all that information. We can still see how it's moving, but you really need these orthogonal views to be able to pull out exactly what vertical, horizontal, and axial is doing at any time. So there's these 4 different things we're looking for. This is the vector plot. You'll go in here first and you'll select, either click select or selection box select. Usually the quick select works the best. I took 5 different measurements that are on this ledge, this plate that's curved here. And I told it I wanted vector plots, and I hit finish, and it goes and cranks that out. So here's my vector plot. And from this is the motor response, and it has a kind of a swaying directional response. It's a twisting motion in the motor platform. Okay, so, and you can see it pretty well. All these vectors are moving in the same direction at the same time, basically. I go back into here. I say I want to reprocess. It'll take me to this screen again, and I can clear all the points displayed. I can put my points in again, and I tell it I want orbits, and it'll calculate that for me. Okay, so I go to finished, and I get an orbit plot. And this is a different frequency. This is first one was at motor speed. This is at the pump speed. So I have a different shape of the motion, operating shape. This is more of a vertical bounce, and you can see the distortion in the decking. That's really what I'm after. There are mode shapes and operating shapes. This is a combination of the two. There are natural frequencies in this support structure that are being excited, as well as just the orbital motion of the unbalanced rotor, or the misaligned rotor. I can do mag and phase labels, same sort of idea. I punch them out where I want them. I click the mag and phase box and say finished, and it'll recalculate. Now this is a little busy, but it does give me a lot of information. So I think I chose, 5 different locations. It gives me an X and Y dimension, and it holds it still. This is a frequency domain animation, so it isn't constantly changing like a time waveform. So I'm seeing a little less than a mil of vibration, 0.8, 8.6, so just under a mil of vibration. I can get the entire spectrum and do an overlap plot or an envelope plot, and it'll tell me, hey, there's 5 mils of vibration at this frequency. But not where I've measured it. There might be this screw in here that's moving on one of the modes, and it might be 3 or 4 mils, and that might be leading all the other points on the structure. Whatever I pick as a point, that's what I'm getting my response at. So the magnitude and phase. Okay. And if they're 0 degrees phase or 180 degree phase, like a lot of these, it indicates more of a straight line motion of the response. Okay. Now I'm going to show you a few of the normal features. The normal exposure, so there's no color put on it. This is the 1 times RPM of the motor and the 1 times RPM of the pump. And we have 2 completely different motions. This is more of a twisting motion. It's still maybe a second bending mode in the deck top here. This is a vertical motion of the motor pitching about a different plane, and it's also flexing the deck. One of the bigger motions is this screw. This is a jacking screw. So we set these up. There's 4 of them on this platform. You turn the threads and lift it up, and that's how they align the sheaves, the belts. Once they're at the location they want and the alignment they want, they bolt it down to the frame here. So there's 2 big bolts in the end here. Then they loosen these up, and now it's an oversized hole with a threaded rod basically jiggling around in there. So it's a little bit of a distraction for this mode. It doesn't show up nearly as much on the motor speed, but it does on the pump speed. How does that affect us? Not too much. Here's the motor speed, and you can see the nut, it's just basically standing still. Over here, it's moving quite a bit. So it's got a lot more motion than anything else in the frame. And it's about 2 mils of motion. Remember, we put our notations on this platform, and we couldn't find anything greater than 1 mil. So, you know, most of that motion's just due to the bolt. And I mentioned earlier, or maybe I didn't, the human eye can only see about a little over 4 mils of vibration before it's visible. So it's usually 3 to 4. In my eyesight, it's probably closer to 5 mils. But you can't see this motion on this nut in an unamplified image. Okay, we haven't enhanced the pixels, we haven't changed the displacements to correlate to that. But now we can see it because we've gauged it up, we've multiplied. So there's same 2 modes, and we can get. I love the color contour. It gives us a better idea of how everything's flexing in one shot. This is the orbit plot. So same deal. I have the motor on the left here, and I have the pump speed on the right. And it gives us more of a lateral indication here by my elongated orbits in the horizontal direction. Here it gives me more of a vertical response in the end of the motor. So it's not pitching sideways, it's pitching vertically in this. And the last one's going to be the vectors. And the vectors give us, again, an idea of the trend in the motion. Here they're all moving together and more of a twist horizontally. Here they're kind of a jumble, but there is a bit of in-phase motion vertically. All right, different frequencies. So what can we pull out? Since I took 2 seconds worth of data, I had really good resolution on the peaks. You know, I could have taken 8 seconds, but it doesn't appear to get me much better definition than that 2 second window. So there's several modes that came out of this analysis of 479, kind of a rigid body rocking mode in the horizontal direction. And you'll notice the plate doesn't flex at all. Here's the motor speed, or excuse me, the pump speed. So there's a natural frequency in the deck at the motor speed, and we're flexing it. So it's a vertical kind of oil can response at first bending mode at the end of the shaft here, or end of the plate that the motor's sitting on. There's another mode at 899, and it is another lateral mode, and it kind of is in this direction, kind of an angle. Okay, And you'll notice this one's kind of an angle, but it's about 90 degrees out. So there is some symmetry here. These are two rigid body motions of the platform occurring simultaneously. This is the motor speed, and we are deforming the deck, and we are twisting the platform. Okay. Now we're going to put some of our enhancements on here. We have our normal exposure for the pump speed. It's basically bouncing up and down vertically. We can see all the color changes occurring simultaneously above and below. We see the orbits are more in a vertical direction, and we can see the vectors are also changing in a vertical direction. This is the motor speed, normal exposure, and it's overall kind of a horizontal motion. The color contour is telling us what's pitching, where's the most motion, and it's in the motor itself, but you're distorting this plate. So the whole platform is twisting as well. The orbit plot shows that more of a lateral twisting motion, and the vectors pretty much show that as well. I was on a job last week, and it was unrelated to this piece of equipment. This is a recovery boiler turbine from a paper mill. And if they lose this piece of equipment, the whole pulp plant goes down. So I had a problem a few years ago on this, and we fixed it. We thought it was a misalignment, but it turned out to be a natural frequency in the structure, and we did some structural modifications to fix it. This is a front leg on one side. It's a 3-point mount. So on the inboard coupling side, there's this mount. There's another one of these on the other, and then out here in the end where the turbine bearing is, there's a triangular mount that's attached to the frame. So it's a 3-point design. What we wanted to try and look at was the coupling, and we had a little passageway that's about 6 inches by 8 inches that cover in the coupling guard that we could look at. And the coupling guard itself is moving quite a bit. So this is on the outside here. This is the spinning shaft in there, and you can see something's going on. The turbine side of the coupling, there's the bolts going by, here's the hub. This is the shim pack inside. So there's distortion in that shim pack. And there's a little bleed over because of the shim. There's just a small crack here between where the hub and the shim pack are. But there's definitely some distortion in the shim pack. And they wanted to see if there was any indication of misalignment problems so they could go in and align it instead of shutting down and maybe having to make a structural modification. And it does look like there's some type of misalignment in here. This is the time waveform ODS, so we're seeing the spinning shaft. This is the frequency domain ODS, and we're seeing the distorted image right there in the shim pack. But this one gives you a much better look at it. I really like this look. I used the orbits and the vector plots to give us a little better indication. This is a time waveform orbit, so this might be 20 or 30 revolutions of the shaft, and it's showing me that orbital pattern here. That one's changing slightly with phase, but everything's pretty stable. But this out here is a much larger response. So I have a bigger circle here. I have more or less straight line motion right there, that distortion, and then it's out of phase. So we're doing some weird wiggle right there in the shim pack. The FFT ODS orbit shows you just basically one revolution. So, and again, it's showing you that distortion going through here. So we're kind of a phase change, or trying to get one right through that that little wiggle in the structure in the shim pack. This one also, the vector plot looks really nice. And a little bit of an enhancement when you're just looking at the vectors going back and forth in the time domain. In the frequency domain, it's giving you a gross response of here's the direction of the motion in any given time. So they both have their nuances. This was a very dark area of the plant. I had my lights on it. It's very grimy as well. There's oil and soot all over this thing. They just had a fire, an oil fire, just a few weeks before that, and it made everything very difficult to view. Documentation. This is the mag and phase labels that you can put on it. So you can pick which points you want. So I took some points on the hub and over on the shim pack. And since it's in the time waveform, it's going to go all the way to maximum extreme to the minimum extreme in the displacements. And that's what we're seeing here. Okay. Normal exposure in the frequency domain, the vector plot. Oop, ODS vector. Actually, I should have said mag and phase, but it'll give me a direct value. So there's 1.3 mils, 1.5. You can see what we got. 0.2. Yeah. So a couple of mils of vibration. So that's right there on the coupling in the shim pack. And what we're really thinking is going on is it's a horizontal offset, but we're not going to be able to see it in this view. But this is the only direction we could actually view the coupling. So we have an indication of an axial distortion in the shim pack and a little bit of motion vertically, but we can't see the horizontal motion in the coupling. We could, however, look at the mounts. This was the outboard mount that was bolted to an I-beam frame. And this is the data that I shot last week. And this ledge that it's sitting on, the I-beam ledge, is flexing. So there is some lateral motion that's consistent with their alignment measurements, or the historical alignment problems they've had with this. This is on the inboard side, the other leg, and you can see that it also has some horizontal deflection in it. Not a ton, about a mil or so, but it could be, you have blue here indicating there's much less motion. Here you have orange and red indicating there is a motion there, and it's not the same across the bolt pattern. So there might have a slightly loose bolt here, and it's tight on the other side. Okay, which wouldn't help the overall alignment either. So probably ought to first tighten these down and see what that does to the alignment and the vibration, and maybe plan an outage. Doesn't look like there's anything real urgent about this, and it's been running this way for a while. So that's going to be my recommendation. This is that third mount. So it looks like this, and the ledge of it is bent 90 degrees, and it's bolted to the frame on the other side. And if you're looking here, this is a close-up of some modifications that we did years ago. This is the top of the I-beam, and that's that vertical mount right there. So from this, I couldn't see a whole lot. And if you turn on the color contours, these lines have so much motion in them that it just distorts everything. So it's really hard to pick out if there's any issue on this mount. Didn't appear to be. Okay, that's basically what I have for today. I do have some training and some purchasing if you guys are interested. The ODS videos, what it costs, and you can upgrade your package if you already have up-to-date user of MEscope software with ODS, basic ODS or better. You get a big discount. You can pick out a camera if you like. There's a couple different Chronos cameras. So the 1.4 is what I use. The 2.1 is the next generation, and they have a little more features in a carrying case and all the good stuff. All right. What I wanted to get to was the training, and I'm putting together a web-based training for MEscope ODS videos. Some of the outline here, the camera basics of the different cameras, the operating software overview, the lighting setup tips, best practices, what angles you want to take your data at. And usually that's logistics are the big problem with getting the right angles on the piece of equipment. Taking close-ups, jitter control, using triggers that are built into the camera, and then using the ODS videos. And I have wizards, scripts, and hotkeys, and remembering that you can do a time waveform animation as well as a frequency domain animation, okay? And they give us different things. And last, data manipulation. So all the features inside the signal processing and the MEscope software is built around ODS. So you get that from the people that invented ODS. We can scale the displacement, velocity, and acceleration. We can move in between them with differentiation and integration. And we can now use some of the stuff that wasn't in the wizard before, but the contour colors, the vectors, and the orbits to our advantage to understand the machine motions. And don't forget, you can use ODS videos for modal analysis. And I've done it several times now in different applications. And you're using the spectrum, the waveform, and the power of MEscope, and you usually have a great outcome. Anyway, if you want this training, haven't properly set the pricing yet. I'm still working it. It's going to be a project-based type training class where we'll get some instruction, and then we'll do some exercises and then go over the exercises and see what everybody did, and walk through the camera, the setup, the wizards, and different animations. Okay, and even though it's not in your plant, or it probably isn't going to be, I will also come to your plant and do it that way as well. But everything's a real application. Wind turbines, pumps, compressors, motors, gearboxes. We've been using it quite a bit, and there's quite an archive of different analysis tools we can pull out. That's basically all I have for this webinar, Mark. If you have any questions, I'd be happy to.
Yeah, there's no questions at this time. You must have done a fantastic job.
I'm getting better at this.
Answer anybody's. If you have any questions, feel free to go ahead and type those in, and we can get those answered right now. Again, we appreciate everybody jumping on the webinar today. And like I said earlier, we are recording this, so you'll get an email with a link to the recording sometime this afternoon. Usually it takes about an hour or two to process from GoToWebinar, but then you'll get an email. No questions. Dan, do you see any? I don't see any on my side. Did you see any on yours? I don't.
No.
Okay. You must have done a bang up job then.
Well, looks like we got 28 people. Not too bad.
Not too bad. Yeah, we had a few more than that. We had about 37 or so. So anyway, well, we can end it there. If you have any questions that come up after you reviewed the webinar, feel free to send us an email. You can shoot those to webinar@vibetech.com, or you can send them straight to Dan at modalguy@aol.com. Again,
did you, Mark, did you still giving a discount or anything?
Yeah, if you do, yes, you can still, if you reference ODS Videos 10, and when you're talk to either your reseller or if you're purchasing directly through our sales department. If you reference ODS 10, we'll go ahead and give you 10% off any of your purchases, and that's for joining us on this webinar. That is a webinar special, so feel free to reference that, and we can go ahead and get you that discount at the purchase of a new package, or an update, or an upgrade package.
Sounds good.
Okie doke. Ramiro says thank you. You are very welcome, Ramiro. Oh, we got a question here. It would be nice that next time you put an OMA case. So that came from Javier. So Javier, we will take that into consideration. He would like to see an OMA case.
An OMA case? Oh, wow, I just did one last week as well. I didn't do it with the camera. It was logistically impossible to do it with the camera, but I did it with an accelerometer, and it was in a paper plant, really awful conditions, but it turned out spectacular. Maybe I'll do it next time. What do you think, Mark?
That'd be a good case study. Yeah, maybe we can jump on that one next time.
And you guys, you think about this, it's a good lead-in for me because you get operating deflection shape. So you can do the MEscope ODS videos, but you can also do an ODS with this software. And that means you can do, you can kind of do operating modal analysis with that as well. There is some curve fitting features you might need, but you can do modal, you can do ODS, you can process data with all the tricks in the MEscope software.
Great. Mark and Javier, thank you. They both said thank you very much. These are very helpful trainings. So we appreciate you guys joining, and we will continue doing these. Probably have one teed up here for the next couple weeks. Coming into the latter part of August, we'll have another one. And if you have any recommendations, yeah, like Dan said, if you have some stuff you're requesting, if you want to see something that we haven't reviewed in previous webinars, go ahead and shoot us an email. And we're always open to suggestions and how we can improve these webinars. So great. With that, let's go ahead and wrap it up. And we will see everybody next time. Thanks again for everybody. Be safe and have a great afternoon.